space technology and machine learning for agriculture. And for this 2 days training, we'll be covering different aspects of space technology and machine learning, which is the new technology for emerging advanced technological agricultural era. So we'll be having with us Dr. Shakti Subburailu, Dr. Prashant Srivastav, Dr. A.K. Verma for 2 days. And in this inaugural session, we'll be having with us Dr. Brian K. Slater. He's currently at Ohio State University, and so I'll start with the invitation to Dr. R.S. Punde for welcome address and introductory remarks for this inaugural session. So may I request Dr. R.S. Punde for the welcome address and introductory remarks. Please, sir.
Thank you, Rucha. Very good morning to one and all. And first of all, in this 2 days webinar on space technology and machine learning for agriculture, very important area and maybe almost unexplored area. And more specifically to this agriculture sectors, I first of all, on behalf of the family of our university, Anand Agriculture University, Anand, and on my own behalf, I first of all welcome my Honorable Vice Chancellor, Dr. R.V. Vyas, who shall be shortly joining us, Dr. Byan, just in a few minutes maybe, he has asked. And he has been pivot of this, not only our patron, but for this.
Vyas sir is already joined.
Sir has joined? Yes, that's fine. He has already joined. And he's not only our patron, but he's the guiding force in this project, and for his encouragement and all kind of guidance in this project. Sir, I welcome you to this today's webinar and this inaugural function. And I also welcome my principal and dean, Professor Jhala, who is not only member, but also officer in charge of this project. And from the day first, he has been involved in all the activities of this project on Center for Agriculture Market Intelligence at our university. I also welcome our national coordinator, Dr. Prabhat Kumar. He also has asked that he will be joining shortly, but may not be, but he is very much there live, and he was asking that he shall be joining maybe a little later. With this, now on behalf of on my own as well as on the family of my university, most importantly, I welcome our chief guest and keynote speaker in today's function, today's webinar, Dr. Brian K. Slater. Dr. Brian, welcome you, and good evening, because that's your side, it is good evening, I think. Yeah. And we are very keen to listen you in this unexplored area, very important area. And today to note down some of the points and the suggestions for improvement as well as learning many things in our project. This is one of the objectives in our this project of market intelligence. I'll be little discussing in brief just shortly, maybe just brief. And I also welcome our Dr. Kathiria, who is Director IT in our university, as well as CCPI of this group IT in our project, which is multidisciplinary projects. And Professor Lart, both are also the joint organizing secretary. And most importantly, I welcome our organizing secretaries, Madam Rucha and Dr. Preeti. Both are here very much with us. I also welcome other participants and all my friends, colleagues who have joined and who are likely to join. And most importantly, the participant who some have joined and some are likely to join. With these things, I would like to briefly tell mainly to those who are joining first timers about this project. Some 1.5 years ago, this project, ICR and World Bank funded projects, our university got. And thus, basically, this is the market intelligence project, Center for Agriculture Market Intelligence. And we are dealing with 4 basic objectives in research: price forecast, demand and supply, mainly to Dr. Brian, towards you, because we are discussing and we are doing many activities here, but because you may not be knowing much about these projects, and some of those who are just joining or who have joined at first time. So 4 basic objectives are there under this prestigious projects funded by ICR and World Bank on 50-50 basis, 3 years duration, and in Indian rupees time it is around 17 crore, to be specific 16.89 crore rupees. Already we have completed 1.5 years, It's very important. Our progress has been found satisfactory. Apart from many activities, two major activities are there. One is conducting research in the broad area of market intelligence, which covers price forecast, demand and supply for crops and allied activities, including price forecast with the help of the satellite data or maybe machine learning, or basically if I say this is artificial intelligence model. And our ISRO is the partner institution in that. We have done some homework, but still we have to go a long way. And Dr. Rucha and other teams, our CCPI, Dr. Kathira is there. They are expert in this area, and they will be discussing little later maybe more about these things. So these are something, and other objectives are global intelligence, including quality aspects, marketing and some other approaches, reforms, and farmer producers organizations, conducting research in these all four areas, as well as conducting capacity building program or training programs like this one for various stakeholders, including farmers. But the focus is on students of higher education, scholars, PG scholars, or maybe MSc, PhD students and faculty members. As far as this activity is concerned, or maybe this is specific objective is concerned, so this is almost unexplored area, at least in India, in agriculture. When we see the literature, though we are not expert in this area, Rucha is there, other than Preeti are there, they have done some good work. They are engaged in 5 to 6 major projects associated with ISRO also. But we are here to learn, because when we review the literature, we will find only few cases are there, but they are not based on rigorous analysis. We are here to understand the methodological aspect, as well as how our students, PG scholars in higher education, as well as faculty members, can understand these methodologies and use these methodologies in their projects, maybe MSc thesis, PhD thesis, and projects by the faculty members for its use or application for farmers as well as policymakers. This is very, very important for us. Only few articles or maybe few papers are available from our side, at least in India, as far as our little knowledge goes. So very interesting for all of us, and we are looking to make use of this methodology, mainly the artificial intelligence models, apart from the models which we are normally using or based on statistical analysis, statistical mathematical modeling. So this is the new area for us, almost new area, and we are calling it again the unexplored area, and we are trying to understand. And from your keynote address, Dr. Ban, we are very much interested to learn few things, some suggestions, and maybe a little later, we may be asking you some questions, may not be right now today because there may be many questions. And we expect something from you as well as from Dr. Shakti and other expert member in this area. And we are also conducting capacity building program, as I told you, in these all areas, including this one. Already we have done some work. And this is just brief about this project. This is a prestigious project, and we are looking how to make it available, or maybe these methodologies, how our students, PG scholars and faculty members can make use of these methodologies in their concerned projects, particularly in the broad area of economics, management, and more especially price forecasting. This is just brief. And with these things, once again, I welcome all the dignitaries, Dr. Ban, my Vice Chancellor, Honorable Vice Chancellor, and other dignitaries, as well as all the participants and my colleagues here. This is at my end. Over to you, Rucha, please.
Thank you very much, sir, for a very nice introduction of the project and welcoming all the dignitaries present here. May I request now Dr. Y.C. Jhala, Principal and Dean of International Agribusiness Management Institute, Anand Agricultural University, to address the present audience here.
Namaskar, good morning to everybody. Our Honorable Vice Chancellor, Dr. R.V. Vyas, respected Professor Dr. Brian Slater, Ohio University, USA, this center's Principal Investigator, Dr. Punir, this coordinator, Dr. Rucha, and all participants. I am very happy that we are organizing such an advanced topic for our webinar. First of all, as a officer in charge, I heartily welcome all of you. This is very good webinars. We have up until now conducted 22 programs, including 10 webinars And it is, I am very happy to announce that total 35,000 are participated in these webinars previously. So this is a very good, in this COVID situation also, we are doing this type of activities, and this involvement is also very high. So it is very beneficial to all of you. Today's topic is also very important to explore the application of artificial intelligence in agriculture and to provide agribusiness manager with an understanding of current and emerging trend and present representative example of popular applications. And we know some popular applications of this artificial intelligence, agriculture robots, that will be very useful in these situations when we are facing the labor crisis. So if we know the application of agriculture robots, it will be very useful, though it is not in a much more popular in India, but nowadays is come to use this agriculture robot also. Then crops and soil monitoring area also. For soil health, some sensors use is very useful. So for irrigation purpose, what is evaporation rate and what time of irrigation is given, for that purpose also, we can use this artificial intelligence. So this is also very important. And so far our project is concerned with that, Dr. Punir has already said that forecastings of the price forecastings, projection of demand and supplies, these all are very important for market intelligence. So predictive analytics is very important. And our partner is ISRO, that you know. So we need such type of immediate data, immediate conclusion. I don't know about this, much more about this technology, but so far economy is concerned, we have data. Suppose we have a cumin crop. So we need the data of our competitive countries. Our competitive countries productions, if we have a data of production scenario, then that will be impact on our prices also, because agriculture prices are now global phenomena. So our competitive countries, what is their situations of this yield, that we can get this such type of data through this remote sensings. And that is why we have partnership with ISRO. So we need such type of technology, we need such type of mechanisms that we can get the accurate predictions about this our agriculture crops, because agriculture crop is very low, its price is very fluctuating, and farmer don't get benefit of this higher prices, when to sell, where to sell, how to sell. This all depend upon the decisions. So for decision making, this in this smart farming, this topic is very important, and how I hope that all the participation will get the advantage, and our future we will develop such a simulation model that will be give perfect decisions and accurate decisions for market intelligence. So we can disseminate such type of information to our farmers, and that will be benefit. So this is our main concern, and I congratulate our this organization of this webinar, that they have chosen the right subject, very advanced subject. And you know, this is the scheme for advanced education schemes. So all our new researchers, new initiative will come, and new thing will learn, and that will be useful for the all. Thank you very much, and I hope that this all will be benefited. Thank you very much.
Thank you, sir. So now we'll move toward our keynote address, and I would take an opportunity to introduce Dr. Brian Slater here. I'll just give brief introduction of Dr. Brian Slater. Dr. Brian Slater is Professor of Soil Resources and Associate Director in the School of Environment and Natural Resources at the Ohio State University, Columbus, Ohio, USA. Dr. Slater received Bachelor's in Agricultural Sciences and Master's in Agricultural Sciences from the University of Queensland, Australia, and PhD from the University of Wisconsin, Madison. Before joining Ohio State in 1997, Dr. Slater worked as a research soil scientist for state and federal agencies in Australia, where he pioneered digital soil mapping in the 1990s. At Ohio State, he has been responsible for teaching courses in soil science, where he has taught pedology, urban soils, soil management, and geospatial information for natural resources. His research interests include digital soil mapping, digital soil morphometrics, soil health assessment, application of remote sensing in agriculture and land management, and classification and mapping of urban soils. It's our great pleasure to have with us Dr. Brian Slater, and I would now request him for keynote address on the topic remote sensing technologies for agronomic and soil management. Please, Dr. Brian.
Good morning, everybody. It's almost morning here. I'm very happy to be here with you. It's a great honor to join this group and in particular to be given the opportunity to initiate this very interesting 2 days of learning. I should let you know, thank you for the very nice introduction. I am not in any way an expert in artificial intelligence applied to decision making in the economic sphere. I am, to use the terminology of Dr. Ratan Lal, who is one of my colleagues at Ohio State, who has just been awarded the World Food Prize. Dr. Lal talks about the importance of a soil-centric view. And what he means by that is that the soil, the resource that I'm most interested in my research and teaching, is central to the continuum or nexus between the biosphere and the other parts of our planet, leading right up to animal and then human health. So there is a continuum between the soil to the plant, to the animal, and to humans, and human health and welfare depends so much on the soil. So that's why I work in that area, and that's where I'm coming from. But today I was given the opportunity to talk about space technology and in particular remote sensing, which is an area I know a little bit about. So that's the focus that I'm going to have, mostly on remote sensing, why it's important and what it can do. And then I know Shakti, my colleague, is going to talk a little bit about some of the applications where also machine learning has been invoked. So I will now share my screen. I hope this will work, and then I can begin my presentation. I hope that everyone can see this and hear me. Dr. Richard, could you let me know that everything's showing up okay?
Yes, Dr. Brian, we can see and hear you also clearly. Okay,
so again, my topic, remote sensing technologies for agronomic and soil management. And basically, I'm going to just give a very brief overview. You could think of this as a bird's eye view, I guess, of remote sensing. This is such a large and complicated area, and there are thousands of new applications and literature that is absolutely exploding in this area. So this is going to be very brief, and given the complexity and a number of different topics, I'm just going to give a very broad kind of overview. Firstly, I'm going to start with some of what I consider the imperatives related to the needs of our environment and human health with respect to why remote sensing might be an important source of data. I'll talk a little bit about applications and then the technologies briefly. I'm not going to go too deeply into that because I'm sure that's going to be explored much more thoroughly by other speakers. I'm going to give some examples, general ones that relate to how people use remote sensing in agriculture, and then mention a couple of more specific examples that relate to my own work. And then I'll finish off with not being totally positive, because there are still many things we need to learn and do. So let me start here. The Sustainable Development Goals of the United Nations. And these are, as we all know, broad goals for what we need to do together as people on this planet to keep our social, environmental, and economic systems moving in the right direction towards the world that we will all be living in, hopefully in 2030. And so I'm not going to touch on all of these, but I did want to mention two in particular. Number 2, zero hunger, and number 15, life on land, because both of these relate to the soil resource that I'm interested in, but also relate very well to data collection and decision-making tools that we're going to be talking about in the next 2 days. So let's go a little bit deeper. So the way the Sustainable Development Goals work is we begin with goals and then we move in more detail to targets, and then there are applications and results. But really, I just wanted to mention a couple of these targets that I think are very important for us to bear in mind. Firstly, the target of sustainable food production and resilient agricultural practices, target 2.4, which involves the idea of ensuring sustainable food production systems, implementing resilient agricultural practices that increase productivity and production, help maintain ecosystems, strengthen capacity for adaptation to climate change, extreme weather, drought, flooding, and other disasters that progressively improve land and soil quality. So when I see this, I start to get this feeling that we're trying to optimize many, many things at the same time. And it's like we are having to get better in so many different areas. We have to increase production, but at the same time, we have to adapt to dysfunctional systems like climate change, extreme weather, droughts, floods, etc. And at the same time, try and improve land and soil quality when we know that the general direction of soil and land quality has actually generally been in the downward direction over many hundreds of years. And then we can see that particularly when we look at this target 15.3 related to land degradation, ending desertification and restoring degraded land. By 2030, combat desertification, restore degraded land and soil, including land affected by desertification, drought, and floods, and strive to achieve a land degradation neutral world. So that's quite a task or set of tasks, I think. We can think about this in terms of many different challenges that we need to meet. We know that we have this rapidly increasing human population that puts demands on our food production systems, on water, on our living spaces, and threatens and impacts natural systems that are the underlying systems that keep our planet working. We know that we have climate change. We know that we have, as a result of both of these, increasing demand for food and challenges to producing it. We know that there is water scarcity and many quality impacts of the things that we do on water quality. Another way to look at this, I think, is to think about these peak ideas. You know, you may have heard of peak oil, and maybe we don't have that anymore, or maybe we do, but I'm convinced, as others are, that we have actually passed peak soil, because we know that soil erosion, salinization, pollution, and the loss of prime agricultural land has increased in many, many places every year. And as a result, we have less and less of this soil resource to deal with, less and less to use, and less quality of soil to produce food and the other ecosystem services that soil and our environment produce. And at the same time, we have massive urbanization, threats from pests and diseases, and many impacts on natural systems. This is perhaps a complicated slide here, but it summarizes a lot of the points regarding these challenges to human ecosystem interactions. And I would like to acknowledge Ratan Lal, my colleague, as the source for this information. So we know we have a rapidly increasing population. Many people have said 2050, we're probably looking at somewhere near 9 billion or more people that we will need to feed, clothe, house, and care for. And perhaps even more by 2100. This puts stress on all of our systems. So if we look at the soil, for example, we know that we have land degradation, about 1.1 billion hectares of land affected by water erosion and significant amounts of land affected by wind erosion. We have 20% of irrigated lands affected by salinization. And as we increase irrigation to meet the needs of more production, then salinization will continue to be an issue in many parts of the world, particularly the tropics and places like Australia and Africa. We have threats and stresses to our water system. We know that many people in many places, many regions are affected by issues regarding the availability of water and competing uses from agriculture to urban systems to industry, and as well as threats to the amount of water. There are important threats to water quality. And then we know that these things are related to climate change as well, so that as climate changes, the planet warms, then there will be major impacts to major water sources like the melting of snow and ice in highlands that provide water for a significant proportion of the world's population. And at the same time, we know that underground and other water resources like aquifers are continually being downgraded. We have the loss of agricultural and natural land to urbanization. The global land area is expected to increase by 152 million hectares, or 10% of the current arable land area. So at the same time that we are trying to produce more food, we are trying to look after natural systems, human population will grow and urban centers will grow at an even faster rate and use up some of the land that would otherwise be available. We have other issues like tropical deforestation, extending in many parts of the world, reducing the capacity and ecosystem services of natural systems, serious losses of biodiversity, and all of this, again, might come back to what's happening with climate change. And Dr. Lal talks about this soil-centric possibility of trying to keep as much carbon in the soil as possible. So we may have lost significant amounts of soil carbon into the atmosphere through land use. It is one of the biggest sources of carbon that's gone into the atmosphere and forced global change. And a significant amount of that comes from the soil. But on the other hand, the soil can be a place where we can sequester significant amounts of carbon, with the payoff being of higher soil quality, higher crop yields, and higher potential for the natural systems in the soil to be resilient. So given all of this, these are enormous challenges for us. And when I think about this, I think about the old story of how we want things better, cheaper, and faster, and we can only pick two. But when I look at those issues and problems and challenges for the future, I think we have to find a way to try to optimize all of these things at once. So what is the approach to these issues? We could, if we think of it as human-centric and think about the food system as a major ecosystem service, then the approach has to be one of sustainability for the food system, and that's going to involve a large number of components that run the gamut from reduction of wastes, keeping the human population as manageable as possible, careful governance of land markets, access, livelihoods and utilization, managing demand to make the system efficient and less wasteful. But from the agronomic and soil perspective, we have this idea of sustainable intensification. So what is that sustainable intensification? That is, I think, one of the solutions to these problems. And I'm moving from this towards technologies. So we could think of sustainable intensification as being utilizing crop varieties and livestock breeds with high productivity ratios to the amount of inputs. So this is something that can and will be a continuous focus of research and management in agriculture. How can we get more from less? Avoid unnecessary use of external inputs, including everything like water and pesticides, fertilizers, for example. Minimize those because there were always off-site and other impacts to natural systems and eventually effects on human health. Harness agroecological processes such as nutrient cycling, nitrogen fixation, predation, parasitism. All of these things are making the best use of natural processes that we need to understand better. Minimizing use of technologies or practices that have adverse impacts on the environment and human health. Minimize impacts of system management to externalities such as greenhouse gas emissions, water effects, increasing things like carbon sequestration, biodiversity, dispersal of pests, pathogens and weeds. And the one that I passed by here, which is the lead in, I think, to talking a little bit about the technologies we're talking about here. Make productive use of human capital in the form of knowledge and capacity to adapt and innovate, and the use of social capital to resolve common landscape scale or the system-wide problems that I've been talking about. So this is where I think technology has a role. The more that we can think, the more that we can apply ourselves to these many problems through research and outreach to management, the more likely we are to be able to meet this almost impossible goal of better, faster, cheaper. So let me move on and talk a little bit about why remote sensing might be part of that solution. Remote sensing enables us to gather data and turn it into information and then knowledge and hopefully wisdom. That process, I think, might use these characteristics of remote sensing for efficiency. Remote sensing can be timely, objective, and has the opportunity to provide information from local to global scales. Remote sensing can also get us to places where we would not otherwise be able to reach from, again, local to global scales. Remote sensing can be involved in monitoring dynamic processes such as plant growth and helpful in estimating important things like crop productivity. We've already heard today about the value in being able to predict or preempt crop productivity issues and problems. Remote sensing can be used to assess the underlying requirements and conditions of the land that are important inputs into crop productivity, for example, soil moisture and irrigation requirements. Remote sensing is involved and can be involved in identifying soil and crop characteristics and conditions. And that's some of the work that I've been involved in my career. Better forecasting precipitation and crop disease, maximizing crop yields while reducing energy consumption and avoiding the waste of farm inputs such as water, fertilizer, and pesticides. All of these things are characteristics of remote sensing that might help us in solving the problems that I've outlined. So here are some of the areas where agricultural applications of remote sensing have been important. And I refer everyone to this particular site for more information along these lines. This is a very impressive set of online learning modules that NASA produces that's free of charge to go to this site and take training. It's a really excellent source of information on remote sensing in agriculture. So major agricultural applications include crop monitoring, market stability measurements and monitoring, and data that can help us move and mobilize humanitarian aid when there are important issues. So crop monitoring might involve everything from understanding crop types, crop phenology, areas of crops, the condition of crops through the growing season, yield, and this should be yield and yield problems, such as floods, droughts, frost, and pests. We can use that information for crop forecasting. Shortfalls in production and food supply, for example, can be identified. These can help us reduce the uncertainty and increase the transparency of the food supply across the planet, help us to be more competitive in places and more productive in others. And as well, where there are problems, where there are high risks, things like drought and famine, we can monitor food security in high-risk regions, get early warnings of problems like famines, which would enable the timely mobilization of international responses in food aid. So all of these are major applications where remote sensing is being used today. In the short time I have for this talk, I have no way of dealing with the complexity of remote sensing and the wide number of platforms and instruments and outputs. I'm going to summarize this kind of briefly, and I'm going to start here. And this is a very simplified summary of what's happened since the first major Earth observation satellite was launched, Landsat 1. And here we can see the increasing number of major satellite platforms that are basically involved in Earth observation, the kinds of remote sensing that has value for agriculture and other issues like conservation. And this in itself is very much a pared down summary because there is a lot more complexity here. And here we see one of the important points, that over time, the number of satellites and the intensity of observation on our planet is increasing almost exponentially. At the same time, there are a variety of different ways these instruments can look at the surface of our planet and what's happening. So here we see just some examples of the kinds of spectral bands or the spectral characteristics of instruments on a number of these major satellites that are that have been available in the past few years. So we can see, for example, the bands on the MODIS instrument, Landsat 8, the most recent of the Landsat satellites. And there are, or have been, hyperspectral systems, and Shakti is going to talk a little bit about our work with Avarice data, which is an airborne hyperspectral system. And I've done work with some of the products of this no longer available satellite that produced 220 bands within the visible and infrared range. So just a very wide range of different kinds of characteristics. And there are many kinds of spectral and other forms of resolution in remote sensing imagery, and there's just not time for me to go into a great deal of detail about that. But if we now expand this a little bit more beyond just those major instruments I talked about, we can see that the complexity and the number of these instruments and how the capacity is increasing rapidly is going to help us in the coming years deal with all of these converging needs in terms of getting lots of data. That, of course, creates the issue of how can we deal with almost a surfeit of data? How do we get all this information together? But here we can see several of the characteristics I want to point out. The number of satellites and the places where they come from. It's by far no longer a situation where the United States is even one of the major players, when so many other countries have instruments on various platforms, and there is a lot more in planning. And this is even a couple of years ago. So in 2008, there were what could be considered 684 Earth observation satellites. There's more than that now. That is somewhere about 1/3 of all operational satellites involved in remote sensing. So those previous ones I'll look at, these are just optical sensors. So basically in the visual and near infrared range and infrared range. So optical sensors, but there are also sensors in the thermal and infrared bands. And again, we see this very rapid acceleration of these instruments and their capacity to perform remote sensing that's valuable to agriculture. And when we get to radar and passive microwave energy scales, and that's part of the spectrum, we can see again, we go from a minimal number of instruments in the 1960s and 70s to many, many instruments and many more being launched from multiple countries in the coming years. So that gives us a sense of the growth in remote sensing technologies. But it's not just the number of instruments. We see rapidly improving, increasing resolution of these instruments. The spatial resolution in terms of the size and extent of the data and its detail. The temporal resolution, how often the surface of the planet is imaged, and how quickly we can get data related to dynamic properties of our planet. The spectral resolution, that is the wavelength specificity of instruments and the number of bands within the spectrum. And finally, the radiometric resolution, the kind of bit depth of the data. And all of these are increasing because technology and our abilities to deal with data have increased rapidly with increased computing power. So here we can see that we have more and more instruments that have much finer temporal resolution. They'll cross their pathway in shorter time periods and more often. And then we have more and more instruments that have very high resolution in spatial scales. And so this is giving us an opportunity to image land-related variables at a much finer spatial and temporal scale. And as well, another area that I hadn't mentioned is being able to develop images of the surface of our planet in terms of its topography. And again, we've seen major increases in the number of instruments and vehicles that are collecting topographic data. So when I did my doctoral degree in Wisconsin in the early 1990s, I had to make my own digital elevation model using a very primitive GPS instrument that we took out in the field and took multiple topographic points and also surveying instruments. And then we built our own very coarse scale digital elevation model to help some very early digital soil mapping work that I did in the early 1990s. But now digital elevation models at very high quality, very fine scale, particularly through LiDAR, radar-based systems, are available everywhere for our planet, as well as satellite-based systems with very high resolution. And these products are increasingly available for people to use. So I'll talk a little bit about some specific satellites, but this is just to give you an idea of the constellation of operating missions currently being used just by one agency, by NASA in the United States. So there are just so many different platforms and different products that can be obtained. Just to give you an idea, this table summarizes some of the many NASA platforms that have value for agricultural applications. So this is one that we've been very fortunate to work with an agricultural university folks, Dr. Rucha and others, because NASA funded with ISRO this data, which we have been using, and Shakti's going to talk about in a little while. So it's not just space technology, but also airborne platforms that are producing remote sensing that's enormously useful and helpful for agriculture. There are many other satellites here we can see, like the MODIS instrument on the Aqua satellite. We have the various Landsat instruments. And again, I'll talk a little bit more in detail, or at least I'll touch on, again, some of these, some of the things that we can do with these. For example, SMAP, soil moisture instruments. There are new missions being planned all the time. And we know that these missions are well advanced because the work on these begins many years before the platform is launched. So I will talk a little bit now about some of the applications of these technologies. So these are major satellite-based remote sensing systems in the NASA constellation. Now, I need to point out, of course, that NASA is not the be-all and end-all of remote sensing, and I'll just, before I go back to that, mention that India is one of the major players in this area. I'm certainly not an expert on your satellites and what they're capable of doing and the data that they produce, but I did want to acknowledge the large variety and quality of the Indian satellite and remote sensing capabilities. But if I go back to what I know a little bit more about, these satellites include multiple sensors. The major sensors, I'll touch on what these are in a little while, but these are many of the product applications, excuse me, that are of use in agriculture. So we have these instruments that are helpful in gaining data regarding the reflectance of the surface. We have instruments that are also capable of modeling evapotranspiration, this being something that is not directly measured by the instrument, but algorithms and machine learning are applied to produce maps and predictions of evapotranspiration. Land surface temperature and precipitation, an important climate and weather-related phenomena that are very important for agriculture, for prediction, for example, for crop yield monitoring and prediction. These things can be obtained from a number of these platforms and instruments. Soil moisture has been a major target of recent instruments and future ones because it's such an important variable. And I'll talk a little bit more about vegetation greenness, which is an indicator of plant health and plant productivity, obviously closely related to things like yield and plant health. And then finally, the structure of the vegetation system. And so these are many of the applications that agriculture can use from remote sensing systems. So let me just touch on, towards the end of my presentation, some of these applications. And again, there's just, in a short talk, there's not enough time to go into a lot of detail about any of these, but all of these things can be and measured, can be and are measured using these remote sensing platforms. So here, for example, we can see the normalized difference vegetation index, an index of plant health or greenness through a number of different years. So we can see the growth of agriculture and the quality of agricultural production over time in different years, depending on climate change. And so we can see this, these contrasts that happen over time. So let's start with the most simple and ubiquitous attribute of the Earth's surface that remote sensing gives us. We can see these beautiful images that relate to crop patterns in many parts of the world. We can see center pivot irrigators here. We can see linear kinds of fields, radial fields here, more normal kind of square and polyhedral fields. And we know that many different applications use this reflectance data. So for example, we can measure that greenness of vegetation, which helps us develop information on phenological stages and transitions. There are many, many products of these, and I'll show you a couple of examples shortly. So we can put these various spectral bands together and have them model out vegetation indices, which tell us a lot about the health of the vegetation. There are many, many, many different instruments and platforms. So, for example, two satellites, Terra and Aqua, have this MODIS instrument, the moderate resolution imaging spectroradiometer, and VIRS, which is really the subsequent instrument onto more recent satellites that update and improve the quality of that kind of imaging. We have Landsat 8, the descendant of many previous Landsat satellites, which now has this major instrument, the operational land imager. We have the multispectral instrument on Sentinel, and we have instruments like Agril, the next generation AVRIS hyperspectral platform, which is an airborne hyperspectral instrument that you'll hear more about shortly. So all of these produce images of the surface of the Earth that are incredibly important for agriculture. And so here's an example of a fairly new product. So the Sentinel satellite produces data, and that can be harmonized with the Landsat spectral data to give things like a multi-temporal enhanced vegetation index. So over time, multiple dates can be combined together to give an output that tells us a lot about the quality of the vegetation and hence things like crop yields. Other things we could measure might include evapotranspiration. Well, remote sensing is probably the best way regionally over large areas and over time to understand the spatial distribution of evapotranspiration, which is very important in understanding crop growth, for example. The outputs of evapotranspiration have to be modeled. They're not directly measured, but they use all of these things that can be imaged in some way through remote sensing: temperature, air temperature, solar radiation, humidity, the reflectance of the surface, soil conditions, vegetation cover. And so evapotranspiration is something that is massaged out of data from all of these different instruments, for example, and programs within the NASA constellation. So here we can see some evapotranspiration imagery from Africa from MODIS. A very broad scale map here showing surface temperature, which again can be which can be understood from data from those satellite images. Precipitation, again, water cycle is fundamental to agricultural production, and so various instruments estimate and measure the intensity of variability of latent heating structures of the precipitation system. So this enables modeling of weather systems as well as the climate, and that can be related, for example, back to soil moisture. And so there are various missions and programs that help obtain information on precipitation. So again, I can only just briefly touch on these many different applications. SMAP was an active passive system that was launched in recent years to measure soil moisture. So at least the passive radiometer part of this works. And you can see some of the product that's very helpful in providing information about soil moisture on broad and small areas of the planet. Just to finish off, I would like to just show a little bit of the kind of work that I've been involved with in recent years for agricultural applications of remote sensing. So we know that tillage is an important aspect of soil health and soil quality, and generally we encourage conservation tillage and minimum tillage, particularly in the kind of agriculture we practice in the Midwest of the United States. But getting a handle on what's actually out there over large areas is quite difficult, and we know that a lot of soil health and conservation conditions, soil erosion, for example, relate to the amount of plant residue cover left during the non-growing time of the year that protects the soil from soil erosion and improves the amount of water input through infiltration. And so being able to measure plant residue cover is an important thing to be able to do and would help us understand the amount of tillage that's going on out in the landscape. So among the things that we did were compare a number of different remote sensing products and some indices to determine how well we could predict tillage. So we went through a number of points in the landscape. It's a little hard to see here, but we had many sample points where we looked at the amount of tillage. We gathered information about residue cover, and we matched that to these indices from a number of Landsat bands and ratios from the thematic mapper and later the OLI instrument. And then we also were fortunate to have a Hyperion flight line image crossing. This is the city of Columbus in the center here, so we didn't gather any information there. Ohio State University is about here. But anyway, we were able quite well to use these this data from that satellite to predict tillage intensity and residue cover. Another example I would like to give really relates to how all of this data can be put together. So this is a digital soil mapping project that I worked on with one of my students and Shakti in East Africa, in Tanzania. And we compared a number of different input sources to help us build digital soil maps of an important irrigated rice area where sustainable intensification was planned. So the Kilimanjaro Valley in Tanzania has very low rice productivity, but enormous potential, plenty of irrigation water, very good soils, but yields are very low. So the goal was sustainable intensification, and we looked at mapping the soils over this valley and different ways we could use different resolutions of data. So we used terrain data and rapid eye satellite imagery to help us model these different soils, and then use that to develop suitability indices for rice right throughout the valley. Finally, I want to mention one area of remote sensing that's less well known, but of very great interest to me, and that is an active form of remote sensing that senses gamma emissions from isotopes, particularly potassium, uranium, and thorium isotopes. And this is very, very useful in mapping soil. So in this photo here in Australia, in this image here in Australia, we can see the red areas have higher levels of soil potassium. These are mostly associated with particular kind of mineralization and rock formations, and it's very helpful in mapping. Unfortunately, this is data that's generally not available with the kind of spatial resolution that we would like. In particular, in the United States, we really only have data on very coarse a very coarse spatial resolution. But we can still see many of the effects that are important, including the different kinds of parent materials for soils and variable productivity that results from different soil quality. Finally, I'll just mention that there are still limitations of satellite data that will be, I think, solved over time with increasing resolution, but there are still trade-offs. It's pretty much impossible to get high spatial, temporal, and spectral resolution at the same time. So spatial resolution is still too coarse in many cases for a lot of the things that we might want to assess in the field. So particularly crop yield over large areas, yes, but over the field scale, particularly small farm fields, these instruments do not have the spatial resolution that we would really like to have. Temporal resolution is still somewhat challenging. Many satellites only pass over the same spot, say every 3 to 5 days, sometimes only every 2 weeks or so. Multispectral instruments still have fairly broad wavelength ranges, and hyperspectral data that has fine spectral resolution generally does not cover the whole planet or large areas, and spatial temporal resolution of that hyperspectral data is limited. If only we could get average quality data everywhere, I think we would be in really great shape to do a lot of the kinds of work in agriculture that we would like to do. And it's in fact difficult to optimize all of these things, spectral, spatial, and temporal resolution, on a single instrument or platform. So there are challenges in corresponding and building models from from these different disparate sources. There are still problems with sensors on satellites and even aircraft related to clouds and vegetative cover, which obscure some of the things we might want. As a soil scientist, I would like to see the soil everywhere, but vegetation can sometimes get in the way. Shakti will talk a little more about that. Large amounts of data exist in various file formats. So with all this enormous number of satellites and different instruments and data, we have a very, very big challenge in bringing the data together. And I'm sure you folks are going to talk about a lot of that in the next 2 days. And knowledge and data and tools, that human capital is perhaps the most important limitation to what we can do with remote sensing. So that's a very broad overview. Thank you very much for the opportunity to talk with you. And I'm happy to answer some questions if that's what you want me to do.
Yeah, Dr. Brian, thank you very much for your very nice presentation, and everyone was very much interested for this informative lecture. I have actually given some questions. I have taken some questions from YouTube live chat, and I have put it in this chat box. You can see there are 2 questions as per PPT. Why Sentinel-2 is not used for vegetation greenness as scientific product?
Yeah, let me I just wanted to read something here. Hopefully I can find it on my other computer. Pardon me for one second here.
Yes.
So I think the reason Sentinel is not used, or generally there's not a greenness product is I think, and I'm not an expert on this, but the spectral resolution, there's 13 bands, but I'm not sure there is the corresponding exact band ratios for greenness. But perhaps Rich, you might be able to comment on that. I'm not absolutely an expert on Sentinel data, but I know Sentinel-2 data can be combined with the Landsat 8 data, and that can be used, I believe, for many greenness ratios.
Yes, and another question is, in which satellite raster data has used?
I'm not able to really understand that question. I mean, I think all of these satellite data sets that I've talked about would be considered raster data pretty much these days.
And which micronutrient cannot be identifiable using remote sensing?
Well, I would suggest that hyperspectral remote sensing, some forms of hyperspectral remote sensing could be used for pretty much developing images of almost all minerals, because there are spectral signatures for nearly every mineral. So I'm not aware of micronutrients that could not be in some way measured, for example, with hyperspectral data.
And how did we use Sentinel for drought assessment?
Well, again, I think in combination with the OLI, you're basically getting, Sentinel has the multispectral instrument on Sentinel let me see. Yeah, has, I believe, a number of 13 bands from the visible to the near infrared. And so it has a temporal resolution of 5 days. And so those particular products can be used to map plant productivity, for example, the health of vegetation over time. So as that vegetation might change in the direction of less health or less greenness, you would be able to assess the areas where crops were not performing well or where they weren't planted. So hopefully that gives you a little bit of an idea. Do we have any other questions?
No, not exactly. These were the questions. Yeah.
Okay.
So thank you very much, Dr. Brian Slater. And now we have with us our Honorable Vice Chancellor of Anand Agricultural University, Dr. R.B. Vyas, sir. So may I request Honorable Vice Chancellor, sir, for the presidential address. Please, sir.
Thank you, Rucha. Good morning to Indian friends and good evening to my US friends. I'm very happy to be with you today in this very important webinar on space technology and machine learning in agriculture. After hearing Dr. Brain, a very experienced person and renowned scientist who has briefed us about the technology and its fantastic applications in agriculture sector, I think I have learned many things. Of course, one more speaker is also there from Ohio, Dr. Shakti Kumaran. I welcome both of scientists on behalf of Anand Agriculture University for joining with us. I'm very happy that our 2 foreign colleagues has joined today to brief our students and some of the farmers and our faculty about what is this new technologies upcoming in agriculture sector and especially useful to the guiding to farmers. I would like to say that Dr. Brain, a renowned soil scientist, will be agree with me that Mother Earth is to be learned properly, which is supporting us, plants, crops, animals, even human, and our whole ecosystem. And for that, see, I remember that 3 decades before, when we started working with ISRO, Anand Agriculture University and ISRO started working together, our main focus was flood, drought, rain forecasting, and other things. But now in the era of precision farming, lot many new applications which Dr. Brain has taught me today. I'm very happy to learn many new technologies, new applications. I'm impressed that this will change the scenario of farming in India, even not farming, but I can say our farm applications and many more things with the newer technology of machine learning. I believe that a lot of big data are generated out of the satellite images, which is useful for this particular project, our NAHEP CAST project, which is forecasting the price. I think the advanced information about the yield and some prediction from the satellite data, if we can get about the yield, we can advise our farmer about how best they can go for the expected price in the market. And especially, I can say that a lot of FPO, farmer producer companies, are coming up in the India, and that companies should have some advanced information about how best they will get in the market after harvest. So these particular technologies, space technology and machine learning, are really very useful for the farmers to earn more. And our ultimate target is to save Earth, save our ecosystem, and also to have our healthy food for us. And for all this, both the applications are very useful. I personally believe that crop diseases, especially when it comes in a big way. For example, this year in India, especially our Gujarat province or state, Gujarat state, we found that a severe attack of locust. And with the satellite information, if we can have a prediction about the locusts, that how they are migrating from Afghanistan and Pakistan to India, some advanced information if we can get with the data available from the satellite images, we can take some precautions and save our crops. Even some diseases. I have seen that when rust is coming in a big way in wheat, in northern part of the country, satellite images are very, very useful. That immediately farmer can take action about the diseases. So pest and disease prediction, as well as the information which has been said by Dr. Brian that about the soil analysis. I can say that on the earth now, with the help of these two technologies, above the ground and below the ground, all information we can get immediately and with all precision with this, both the technology, machine learning and space technology. I remember one farmer who came to me 10 years before to our university business incubator with a very vague thought. He said, sir, instead of wheels, I would like to have legs in my tractor. I said, what is the interesting thing you are talking with me? I said, let us contact some Japanese scientist who can make your tractor a robot. And it was a really vague idea, but he made it possible. He converted his 4 wheels in legs. And he said that, sir, with a mini tractor with 4 legs, I can do many operations in the field. Even 10 years before, I remember when I went for some toy for my grandchildren, I was trying some battery operated helicopters, which was to be fly. And the kids get enjoyed, oh, something is flying with light. But now the drone technology is very, very important from agriculture sector. So these are the machine learning applications which is upcoming in agriculture sector. Of course, as a microbiologist, I know that when I was studying soil microflora and fauna, even nematodes, it was very, very difficult of identification part. And a lot of hours I have spent on microscope watching the nematode, their characteristic and deciding. But with now having the this all new applications of AI, we can have the ready data feed it in the computer. We can attach a camera directly straightway with our computer, and we can judge how many different type of fauna is there in a small Petri plate. So these are the some of the upcoming applications, and these all automations will definitely smoothen the life of the mankind, even the farming community. And I can say that a lot of newer programs are coming up for to save our precious crop, ornamental crops. Even in India now, protected cultivation is upcoming, and for protected cultivation, I think both this application of space technology, machine learning, and AI is very, very important, because our country's Prime Minister Sri Modi's aim is to double the farmer income. And for doubling the farmer income, forecasting, precision farming, and advanced information about the price forecasting, if 3 can be linked out of this, some of the experts' view, if some points can be drawn out by Dr. Pundit. Dr. Pundit, you can have some recommendations out of this special your webinar.
Yes,
and
sir,
such recommendations we can put it on paper to the council also, that if we can link these 3 properly, we can increase the farmers' income, which is the ultimate aim of us. And so I have been given some points. Many applications are there about the machine learning, like species breeding, species recognition, soil management, water management, yield prediction, crop quality prediction, even disease detection, weed detection, livestock production, animal welfare. Everything has been included and also nicely explained by the in the keynote address by our chief guest, Dr. Brian, today. So I'm not going in detail of that, but all these applications will definitely be useful to us, the mankind, and ultimately to have to grow best, grow better, and to feed our increasing population properly. With these few words, I thank you all the organizer for inviting me and joining this seminar, especially webinar, where I will learn something new applications from my US friends. Thank you very much.
Thank you very much, sir, for giving your valuable time and being present here, sir. It's our pleasure to have with you here. Now, may I request Dr. Y.A. Lard for conveying vote of thanks.
Namaste everyone, respected guest and participant. Myself, Yogesh Lad, Associate Professor and CCPI HRD Group under Nahab Caste Project AU Anand. I feel extremely obliged and honored to propose a vote of thanks. First of all, I would like to thanks our Vice Chancellor, Dr. R.V. Vyas sir, Anand Agri University, as a patron, as well as the person who has given his wishes, Dr. R. Segra, DDG Education and National Coordinator NHB Caste, and for their interesting and thoughtful, provoking address and wishes. I would also like to thanks our chief guest and keynote speaker, Dr. Brian Slater, Professor, Associate Dean, College of Food, Agriculture and Environment Science, Soils, Schools of Environment, Natural Resources, Ohio State Agriculture, Ohio State University, USA, for his keynote address in remote sensing and technology for agronomic and soil management. This may be helpful for the further application in our project. It's our thank you very much. I would express my profound gratitude to our PI, Dr. R.S. Pundir, for his continuous support and guiding for that. I would also like to express our gratitude to Dr. Dhaval Katheria, CCPI of the IT group, for his continuous guiding and allowed the young leader to do this online training program. I would also like to express my thanks to the two organizers. We see both have played a vital role for organizing and inviting and they both have put their valuable efforts and which make this event going to be happen. So thank you everybody for that. It is over to Madam, to you. Thank you very much.
Thank you, Dr. Lal.
May
Yes,
I request you to interact with Dr. Brain and Dr. Sakti Kumaran?
Yes, sure, sir.
Give me 2-3 minutes.
Yes, sure, sir.
May I interact with them directly?
Yes, directly.
Dr. Brain and Dr. Sakti Kumaran, I'll be happy if you can develop some joint collaborative projects with our scientists. We will be happy to work with you, and we can fetch some fund from Indo-US bilateral fund, which has been managed by UGC. If our scientists can assist you, and we can develop some collaborative project, because I remember, Dr. Brain, that when I was doing my doctoral in 1988, I was working on Japanese beetle larva here in India to control the Japanese beetle grub with microbes. That was my theme of my research. So I was at that time interacting with few scientists at your state, Ohio, and especially the area Connecticut, the area where this particular Japanese beetle having severe attack on the crops. So at that time I was interacting with them, but now I can say that some of the colleagues who are working on soil sciences and especially for weather forecasting and with the ISRO, especially Dr. Rucha and others, if we can develop some collaborative project, I'll be very happy, sir. Please. Yes, Dr.
I'll answer first, and I'm sure Dr. Sakti will answer as well. But we would be honoured, and I want to say that when we visited India last year, it wasn't. We learned every single day, every single moment, and I was most impressed by Dr. Rucha's team of young people that went out in the field with us and worked with us. They made our project not only fun, but they made it successful. So any opportunities that we could have to develop any kind of joint work would be absolutely, we would welcome that, I'm sure. Thank you.
Thank you. Yes, Dr. Sakti Kumaran.
Yes,
from your side.
Yes, Dr. Rucha, did you mention did you mention to Dr. Vyas that we were there last year?
Mm-hmm. Yeah,
okay.
Rucha briefed me about you.
Time actually working with Dr. Rucha and her team. So like Brian mentioned, I think Brian, were we there almost for a month or so, I guess? Close to a month. So
perhaps, yeah, 3.5 weeks or so. The time went by very quickly, though, except the days in the field, which were pretty hot.
Yes, sir. My request is some of the common interest, some topics which is common or same problem in Ohio and Gujarat. We can identify such thematic area and have,
I'm sure.
and we can develop some common proposal, funding proposal internationally.
Do it.
Will it be possible? Please
Absolutely.
see the possibility.
Let's do it.
Yeah.
I already told Dr. Shakti that I want to travel back as soon as we can, and we should would have that opportunity, and then we can discuss and develop some projects for sure.
Sure.
Yes.
In fact, Brian, Dr. Vyas, I'm from Central State University. I was previously at Ohio State University. Brian was my advisor, actually, PhD advisor. And so recently, Brian, I think I didn't talk with you about this. The 80-90 institutions in Ohio, I mean, in the US, that we're putting together a center of excellence for global food security and defense. It's funded by USDA and NIFA, but it's primarily, geared toward 80-90 institutions. So, and in fact, we have an Asia node actually. So I'm working with the Caribbean cluster there. I'm looking at Bahamas and a few other Caribbean countries. And the team that I'm working with is also working in Asia, and we have an India node actually. So that's something, maybe I'll discuss that with you, Dr. Rucha, at some point,
So nice as we both of the scientist friend. We'll be very happy to receive you again at India, and we can develop something together for solving the problem of farmers and also for healthy food for all of us. Thank you.
Thank you, sir. Thank you very much for your precious time. And now, with your due permission, we'll move towards session 1 of Dr. Shakti Subburailu, and he'll be going to talk about Ohio-Gujarat remote sensing for agriculture partnership. And let me take an opportunity to give brief introduction about Dr. Shakti. So he has completed his bachelor's in agriculture and master's in soil science from Tamil Nadu Agricultural University, Coimbatore, and PhD in soil science under Dr. Brian's guidance in this Ohio State University. And his expertise lies in soil fertility and nutrient management, digital soil mapping, impacts of agriculture practices on environmental quality, machine learning and image analysis, ecosystem modeling, and GIS applications for natural resource and ecosystem management. He has received more than 12 research grants from various agencies as principal investigator, and he has completed many of them, and some are in progress. He has very good academic experience, starting from junior research fellowship in Coimbatore to currently he has been in the position of research assistant professor of soil science and agronomy at Central State University, Ohio. And he has many publications in reputed journals to his credit. So I feel, and I'm very overwhelmed to welcome Dr. Shakti Kumaran Subburailu for his expert talk on Ohio-Gujarat remote sensing for agriculture partnership. Please, Dr. Shakti.
Yeah, thank you, Dr. Rucha, for that wonderful introduction. Before I begin my talk, may I ask Eric? Eric, do you have your video on? Can you put your video on for a moment? I want to acknowledge my postdoctoral researcher, Eric Salas, Dr. Salas, who is here with me. Yes, there you go. So Dr. Salas was also there with us last year, when we visited Gujarat, and when we were there for like a month or so. And Dr. Salas, in fact, you arrived in Gujarat before we did, right? I think you were there.
Yeah, I spent like a month or so. It seems like I lived in Anand for a while, for a month. So it was really a nice experience for me. Yep.
Yeah.
Almost a month.
Yeah, Wonderful, Dr. Salas. Thank you. So let me see if I can share my slide here, and I'll get off my video and then I'll focus on my presentation, and then I'll turn my video back on once I finish my talk. Let me see. Interesting. Where is the share button? Oh, there it is. All right, can you all see my slide?
Yeah, it's visible now.
Okay. So first of all, I'd like to thank the organizers of the NAHEP and CAST project for providing me the opportunity to talk to you all about the remote sensing for agriculture partnership that we have with Gujarat, actually more specifically with Anand Agriculture University in Gujarat. And of course, our partnership is with the Indian Space Research Organization and NASA as well. Because the work that we're doing with AAU and ISRO is actually funded by NASA. So I'd like to take this opportunity to really thank the support that we have received from NASA. Thank you, Dr. Rucha, for inviting me to give the guest lecture today. The partnership is primarily about mapping agricultural systems in Anand, Gujarat area. And I'm going to be, I'll share a little bit about how this all started. And but before I venture into that, I'd like to take a step back and look at some of the things that Brian talked about, and also how the work that we're doing relates to the topic that we're going to be discussing today, which is the application of space technology for agriculture and using machine learning, right? So if you look at this slide here, this is a recent report from UK Space Agency International, and Brian touched on many of these subjects here, but I want to highlight a few things here. As you can, I don't know if you can see my pen markings there on the screen. Let me go back.
Yes, we can see that.
Okay. Hold on for a second. So if you look at the illustration that is provided in this report here, this is a recent report that was written in 2018. We have these broad agricultural challenges. On the top, you see broad agricultural challenges. And then you have, we have some actions that we could take to address those agricultural challenges. And at the center is where you see the space solutions that we have, right? That how space technology can assist us in, coming up with these solutions, and how machine learning can assist us in that area. And then you have broad outcomes and impacts here. And if you look at the agricultural challenges, of course, Brian talked about hunger and malnutrition. Population growth is another one, and unsustainable use of natural resources, and then of course the one that we cannot control, which is mostly control, which is climate change. So the actions to address those agricultural challenges would include how can we increase productivity, and how can we increase the supply chain efficiency, that relates to the marketing issues that Dr. Pundir talked about, And then how can we sustainably manage our environmental resources while we are focusing on improving our productivity? How can we manage our environmental resources sustainably? And of course, building resilience to climate change. But when you look at all these things, at the center of all of these is the EO products, space solutions and the EO products that we have. EO data, Earth observation data products that we have are products that are useful for credit management, products that are useful for decision support, and products that are useful for insurance products and insurance areas, and also for early warning systems. We talked about all of those things. But at the center, I would like to focus on this area, which is decision support tools. In the decision support tools, like, if we have to think about how can we do price forecasting, right? In order to do price forecasting, we have to begin here. Actually, we have to map out the field boundaries, and we have to identify our crops in the field within those boundaries. Those are two critical Earth observation data that we're really interested in to begin with. If we have to be using or applying space technology and machine learning to solve some of the problems, agricultural challenges that we have regionally, nationally, and globally, right? So I would like to begin with a couple of examples. What you're seeing there on the screen is what is called as the cropland data layer. Cropland data layer. These examples are from the U.S. So United States, especially United States Department of Agriculture, has been National Agricultural Statistical Service, part of USDA. It has been working on developing these layers, a cropland data layer here. And they've been doing this since the 1990s. So for the entire conterminous US, as you can see, you have crop types mapped. The underlying satellite data that's being used to achieve this is our Landsat data. So as you can see, I want to highlight a couple of things on this slide here. The green and yellow portion here, right? It's called the Midwestern United States, Midwest, and Ohio is part of the Midwestern United States. And the green and yellow dots that you're seeing there are essentially corn and soybean. So mostly corn and soybean in the Midwest. And it's also called as the Corn Belt. But you can, if you go out west in California, you can see lots of other crops, vegetable crops and fruits grown. You can see multicolored areas there. So this data that you're seeing is readily available for anyone to download. So this is freely available data using Landsat imagery. Anyone can use it for any purpose that they seem fit. But let's keep this in mind. This data layer is very critical. And then I'll go to the next slide. If you look at this, this portion of the slide here, it says satellite tracks status of nation's food supply. This is from NASA. So they use this very valuable piece of information to really assess the food supply on a national scale. Okay, this is another data that's very, very helpful, useful at the national scale in the United States, which is the common land units data. The common land units data is generated by Farm Service Agency, which is also part of the United States Department of Agriculture. It is essentially an individual contiguous farming parcel, which is the smallest unit of the land that has a permanent contiguous boundary, common owner, common producer association. So it's essentially like, delineating field boundaries. The source for this data is the NAIP or NAIP, National Agricultural Imagery Program. So, which is also run by a Farm Service Agency. And NAIP is administered by USDA's Farm Service Agency. They acquire aerial imageries during agricultural growing season in the continental US. The primary goal being that, the primary goal of the NAIP program is to make digital orthophotography available to government agencies. And especially USDA here uses that information to come up with these delineations or parcels or farm boundaries. Okay, so how did they, how did we, come up with these delineations in the US? This is essentially, a digitized version, it's not like, we didn't use any machine learning to create all these polygons. The polygons were created manually using a digitization initiative. So these polygons were delineated manually. And Brian might like this, slide here. It's ePaddocks. This is from Australia, which is it's a very similar product to common land units that we see in the United States, right? You know, paddock level monitoring, you have these boundaries again. This is available for a cost. You know, if you want have a sample, you could request a sample. But if you want to get the coverage of paddocks for the entire nation or for a region, you have to pay. The prices, I think, you know, for the national scale, it is about 20,000 Australian dollars because it's generated by a private agency. So this is another example, but in this case, they have used a machine learning to delineate all these polygons, field boundaries that you're seeing on the screen. Unlike the common land units, which is manually delineated, but this slide that you're looking at, you know, in Australia is it's developed using machine learning techniques. In fact, they have used neural networks. I think one of the speakers after me will be talking about neural networks, and they've used neural networks to map these polygons here. Of course, the goal is for crop identification, rural intelligence and portfolio analysis, and paddock level monitoring. If you look at this, the information here, even the common land units information, you see these polygon boundaries. Usually Farm Service Agency, what it does is takes these polygon boundaries and ties all the attribute information that is pertaining to or relevant to each farm field there. And they use that information for conservation planning or decision planning programs that the Farm Service Agency rolls out. What do we mean by conservation planning? Like, let's say if the farmers are interested in conserving the land, improving the health of the soils, they would be, given subsidies to adopt some of the conservation practices, like let's say grassed waterways or no tillage and stuff like that. So this piece of information is very useful, and it's available for the entire conterminous US. So let's talk about something very similar in India, right? And I was trying to make a comparison between India and US in terms of the hectares, right? The land holdings, and try to understand some of the challenges that we might face when we have to develop a similar product in India. So the average size of farm holding in the US is 180 hectares. And if you look at the average size, this was from the census data, Indian census data, is about 1.08 hectares. So it's almost like 100 times bigger, the average size is, or maybe even 200 actually. So, and then if you look at the number of farms that you have in the US is 20 lakhs or 2 million farms. 20 lakhs, I used lakhs so that, it might be understandable, a bit more understandable for our Indian audience. So 20 lakh farms. Whereas when you look at the number of operational land holdings, according to the census, right, is 1,570 lakh operational, land holdings in India. All right. And the total number of hectares that are cultivated in the US is 364 and 157. So, and if you look at, I zoomed into the Midwest area, and you have these corn and soybean, green and yellow areas. And then this is an area in Gujarat. On the right-hand side, you see this is an area in Gujarat. And this is something that we mapped. And you can see the different colors representing different crop types that are grown. So the crop diversity is, very high, right? And the fragmented nature of agricultural landscape is another challenge that we might encounter if we have to develop a product like that in India. All right. And then we have variable planting and harvesting dates in India. And of course, mixed cropping. That's something that we noticed when we visited India. And when I was in India, I'm well aware of that, mixed cropping systems in India. So those are some of the challenges that we might have to address or face when we think about, delineating field boundaries or crop type mapping. So the talk that Dr. Rucha wanted me to give was about, the partnership that we have with AAU. and specifically focusing on application of machine learning for crop type identification and soil carbon or carbon sequestration mapping in those agricultural systems. So if you look at this slide here, then you might, see some of the challenges. Already you might start seeing some of the challenges that we might have to face if we have to do crop type identification at the national scale, or regional scale, or at the national scale in India, right? And these are some of the issues that we would run into. Okay, so what do we do now? Machine learning can come to our rescue for sure. Brian talked about that. Just like space technology has its own limitations, machine learning also has its own limitation, but it can certainly come to our rescue. Machine learning algorithms, essentially mathematical models based on sample data. We provide the algorithm some training or sample data, and what the machine is going to do is take that sample or training data, and it's going to make predictions or decisions, for us, on the target classes or objects that we're interested in. So when space technology is combined with machine learning, it offers a potential solution. If you look at machine learning, you can, really classify machine learning into three major categories, right? Unsupervised learning, supervised learning, and then reinforcement learning. Reinforcement learning is the good example would be gaming AI, gaming artificial intelligence, right? Or autonomous vehicles, for example, we use reinforcement learning there. And we have unsupervised learning, which is essentially like, the classic example is clustering, where we have training samples, but we don't have associated class labels or target labels that we are trying to classify using machine learning. And then the more general or the more prominent one, especially the ones that we would normally use in space technology for agriculture, is the supervised learning, and classification and regression are the two broader categories under that category of supervised learning. Okay, so are we there yet? That's the question that we have to ask. And I think Brian mentioned this. We're not there yet, but we're making some good strides. We have made some good progress. But like satellite imageries and satellite technology, for machine learning, we have our own problems, and we have our own issues that we have to deal with. Some of it comes with its own challenges there, right? So the input data for machine learning and application of machine learning in space technology is essentially spectral bands, and Brian elaborated on those spectral bands and also the derived values from spectral bands that we use for making those predictions or making those decisions. So we're essentially using the help of the computer to train. We provide the computer the training data, and we are relying on the computer to train on the data and help us to provide those predictions for the target classes that we are interested in. Okay, and then the other thing about machine learning is there are several machine learning algorithms, each with its own advantages and disadvantages. That's important to keep in mind. And then these machine learning algorithms really rely on if combined with satellite technology, or if combined with remote sensing technology, they really rely on spatial, spectral, and temporal resolution of those the space information that we are providing into the machine. So in other words, garbage in and garbage out. So if we don't provide enough information, then we're not going to get good predictions about the target classes that we are interested in. Okay, and then so you have the spatial, spectral, and temporal resolution, but also the target classes themselves could impose some problems or issues there. If the separability of target classes is not good enough, using the spectral signatures that we get from our satellite products or from remotely sensed products, then we're not going to be doing a good job of predicting or making decisions about the target classes, and the target classes could be crop type determinations, or it could be pest and diseases monitoring, or whatever we are interested in when it comes to using these space technology and machine learning for predictions and decision making. So, and then of course, the other thing is when we try to predict, or when we try to make decisions about multiple classes simultaneously, and when we provide, like I mentioned, machine learning relies on the training data that we provide the machine. So if our training data is incomplete and inadequate, then that's going to also cause us problems. So these last two problems, Brian might attest to this, we're not strangers to these two problems, multi-class classification issue and incomplete adequate training data. So as an example, I want to show this map and highlight some of the work that we did, Brian and I did during my PhD and beyond my PhD. We worked on mapping soil series in one of the counties. County is equivalent to district in India. County in the US is equivalent to district in India. So we were working on mapping the soil series for the soil series for the soil scientist out there in the audience, or the pedologists there. They might know soil series is the finest taxonomic unit in the soil taxonomy, right? Finest taxonomic unit. So when we were trying to map soil series in a county, we had about, I would say, like close to 40 series, and we were trying to map the 40 soil series in that county using machine learning. And the algorithms that I was using were random forest and classification and decision trees. Those are the two algorithms that we were using. But we had tremendous issue with actually mapping all the classes simultaneously, because some of the classes were well represented in the study area and some of them were not. And some of them were actually minor classes, and some of them were major classes. And when you develop these training samples from the study area that we're interested in, some of the classes were represented much more than some of the minor classes, So we ran into this data imbalance issue, and then, this issue of data inadequacy, when we were trying to use machine learning to map soil series at the finest level. So the work that we're doing right now is actually using a hierarchical approach. So Brian is actually, it's the brainchild of Brian. Brian's idea is that, rather than mapping soil series at the, all of them together, why not we use a hierarchical approach? In other words, it's something like divide and conquer rule. Let's map the broad systems first at the top, and then the broad systems, and then we map the subsystems, and then we map the soil series within those subsystems. The broad systems in our case was the soil landscape systems. As you can see on the left, you see an image of the landscape systems here, which is Ohio soil systems here. We have mapped, for example, Lake Erie, system, glacial outwash, and glacial till, alluvium, water, and all that. So you see all those broad systems being mapped. So in order to map the broad systems, we used a object-based image classification, object-oriented image classification to map these broad systems. And then within those broad systems, our next step would be to map the catenas. Catenas are essentially geographically associated soils, map those catenas within each of those systems. So we have about 100 catenas in Ohio that we would like to map. So we map the 15 landscape systems first, and then we map the catenas within each of those systems, and each would have about 10 catenas or so. And then within those catenas, you map the soil series, and each catena would have about like 3 soil series or 4 soil series that we have to map. So by following a hierarchical approach, we are able to, address the problem of data imbalance, address the problem of inadequacy. Okay. So the reason I talked about this work that we have done in Ohio is, just to show you there are multiple ways by which we can address the problem of data imbalance. I'll move on to my work here, like, the work that Brian and I and Eric have been doing, here in Gujarat. We have a similar problem here when we have multiple crop types that we are interested in mapping, right? The focus was to use machine learning to map the different crop types in the Anand district. So we had received a set of ground truth information. Initially, we got like 59 points, 59 data points, ground truth data points. And then later, Dr. Rucha was able to provide us about 115 ground truth data points for crop types in the area that we were working on. But some of them were well represented and others were not represented really well. We ran into the same issue of data imbalance when we were trying to map crop types using machine learning. But before I start talking about the project itself, I just wanted to briefly mention how it all started, right? So this the partnership that we have with AAU and ISRO essentially started off as a partnership between ISRO and NASA. This was in the year 2016, approximately 2015 and 16, when NASA and ISRO decided to partner to collect airborne visible infrared spectroscopy data over many regions in India. And you can see some of the flight lines here in near Gujarat, right? And the purpose of that was, not just agriculture, but also forests, and you have mineralogy work, and there were also hydrocarbon alteration work that is happening using Everest data. So multiple themes, but agriculture was the theme that we chose, and NASA put out a request for proposals to US investigators to work collaboratively with Indian researchers. So that's when, because Brian and I were working on the soil mapping work already, we decided to apply to this funding opportunity with NASA. That's how our partnership got established, where Dr. Bimal Bhattacharya at ISRO provided Dr. Rucha's contact, and we made those connections, and we started to partner together on this project. So average imaging spectrometer, just so you know, we have about 480 bands. Actually, the spectral range for that, for this image is 380 nanometers to 2510 nanometers at a 5-meter nanometer spectral resolution. And of course, the spatial resolution, here it says 2 to 8 meters. And I think, the product that we received was somewhere around 4 meters. So like I mentioned, we received 115 data points for the study region. The first specific objective was to really, map crop types in the study area that we were working on. Okay, the problem with using hyperspectral images for mapping crop type is most methods, machine learning methods, you resort to using average spectral information. Most even indices use average spectral information over broad, wide bandwidths, causing us to lose some crucial information in contiguous bands. So if you have a multispectral band, you're focused on only certain parts of the bands for developing indices that are predictive of, let's say, crop determination in this case, right? So when we do so, we lose those spectral information available in the spectra from hyperspectral images. And we also drop the discriminative power when it comes to target classes with comparable spectral responses. Let's say you have 2 target classes that have comparable spectral responses, then we lose the discriminative power if you're focused on certain bandwidths, which is what is normally done when we use broadband indices or narrow band indices for that matter. Okay, so here is where Dr. Salas's input, plays a very important role, right? He developed this this metric here. We use several metrics to map crop types in the West, in Gujarat, in Anand district in Gujarat. But this particular metric here, it's called as the moment distance ratio, right over left pivot. So this is a very critical or important metric that I want to highlight, that Dr. Salas, proposed, and he developed this metric, and we have used this metric in our study. So what this does is, rather than using specific bands and computing indices using those bands, this metric essentially captures the shape of the entire spectral signature of the hyperspectral imagery. So that is the big plus or big advantage with this metric that we used. So the way it does is, it's Dr. Salas has he has named it as right pivot and left pivot. Essentially, what it is doing is it is calculating these diagonals. As you can see, diagonals, values, the length of these diagonals using Pythagoras theorem, and it summarizes those diagonals. And then the summary of those diagonals is essentially giving us a metric that kind of like quantifies the shape of the spectral signature itself. I don't want to go into the detail of the metric. I'll leave that, I'll ask Dr. Salas to, answer any questions you might have, on that. But to simplify the entire thing, is that it essentially, takes the entire spectral curve and turns into a metric, and that metric essentially, quantifies the shape of the spectral curve, and it uses Pythagoras theorem. It computes the length of the diagonals using right pivot value and left pivot value, and summarizes, and we get this MDRRL metric. But where is this useful? If you look at this image, we worked on using MDRRL in another project where we used high-dice and average imagery that was taken in the US. What we were trying to do was differentiate no tillage, corn no tillage, and soybean minimum tillage. If you look at those images, they look pretty similar. And if you look at the spectral curve there, hyperspectral curve for both corn no-till and soybean minimum tillage, both are different crops, but the tillage looks very similar, right? In both pictures. So it's harder to differentiate between corn no-till and soybean no-till if you essentially just use the spectral signatures that we have, or the specific bands in the spectral signature. So with Dr. Salas's metric, essentially what it would do is it would take into consideration the entire spectral curve and the shape of the spectral curve, and creates that metric that is very helpful in differentiating those two target classes that have very similar spectral signatures. So in this case, as you can see, it's very obvious here that there is a big separation right here when you use MDRRL to separate out corn no-till and soybean no-till using the pivot method. So this is a novel metric that we introduced in our method. So the advantage with this metric is that there's no limit to the number of spectral bands that we could use. What I mean by that is, this pivot values could fall anywhere. So if we are interested in specific portions of the spectral signature, we can essentially use those portions as the bounds for our right pivot and left pivot, and compute the metric that would indicate the shape of the curve. So there are no limits to the number of spectral bands that we could use to create MDRRL values. It is a viable strategy, like I said, in this picture, as you see, for agricultural tillage mapping. So with that metric, we were able to publish our work in the International Journal of Image and Data Fusion. So you can see Dr. Salas is the main author there, and we have Dr. Slater, Dr. Zhao, and Dr. Bhattacharya and others, including Dr. Rucha Dave, and then Parsh from AAU on this paper. So the objective was to really develop and apply a novel approach for mapping agricultural systems using a set of classifiers. Well, I'll talk briefly about the classifiers that we use to map crop types in Gujarat. But the challenge that we were running into was the limited field presence data of target classes. We had only 115 target classes that we were able to use to predict the crop type information in the study area. With the use of spectral information from airborne hyperspectral imagery, right? That was the objective. So we wanted to maximize the use of hyperspectral imagery using the index that Dr. Salas had developed. If you look at the method, this is a quick overview of the methods. The hyperspectral images were processed. We got the average NG data at the L2 data level, and we had to mosaic the scenes. I think Dr. Salas had to take information from 3 flight lines, and he had to mosaic all the scenes. And then he had to subset the study area because, the ground truth data information were limited to a certain portion of the entire study area. So he had to do a subset of the study area. And then he derived all the vegetation and tillage indices. I'll share in a moment the vegetation and tillage indices that we developed and the classifiers that we used. The first step was to, once we developed all those, we used those indices to segment the entire image. So again, here we were using an object-based, rather than using a pixel-based approach, we used an object-based approach to really arrive at the segment, arrive at the segments in the imagery. So once the segmentation was done, this is our one-class modeling approach. This is another unique way by which we can address the problem of data imbalance, a one-class modeling approach. Previously, when I talked about soil series mapping, we talked about, what Brian and I, we did at that point was, we were focusing on we would try to use a hierarchical approach to mapping. Before that, we also actually created uniform distributions of the sample points rather than, random sampling to address the problem of data imbalance. But another way to address this data imbalance issue when you have multiple classes that we have to predict simultaneously is following a one-class modeling approach. So the field data input were fed into the statistical models, and the different metrics were evaluated, and then finally the one-class mapping approach was the product of the one-class mapping approach was a class probability for each of the crop types. And once we have the class probability map of each of the crop types, we converted that to a single multi-species map for the study area of interest. So I talked about this 150 presence points for 5 target classes. We were focused on wheat, tobacco, legume, and eggplant, and others would include sorghum, lemon, papaya, mustard, tomato, and chili, because we had very fewer number of target classes in those, so we had to combine them into others class category, and then we try to map these crop types. Like I said earlier, we used 3 average NG flight lines, to do this. This is our study area, and this is how the points were distributed, ground truth points were distributed. The 7 narrow and broadband spectral indices that we used included a normalized difference vegetation index, which is the most common one that's predominantly used. And then we have the enhanced vegetation index, EVI, cellulose absorption index, which is pretty useful for tillage mapping. Brian, I think in his work, he used CHI, which is cellulose absorption index for tillage mapping. And then we also used SINDRI, which is the shortwave infrared normalized difference residue index. and lignin cellulose absorption, LCA, photochemical reflectance index, PRI, and then we finally added our novel index, which is the MDRRL index. We used 4 models, learning classifiers, 4 different learning classifiers, and 1 ensemble model. In fact, we used 5. One of the models didn't fail to predict, so we restricted our modeling to 4 models and then an ensemble model. When we say something as an ensemble, which is a combination of all 4 models, you know, it's sort of like an average of all the models, all the other classifiers that we used. In the 4 machine learning models that we used, you know, we used the generalized linear model, random forest model, which is a multi-decision tree model, and then you have the maximum entropy model, and then the multivariate adaptive regression splines. Without going into the details of the models, these were some of the classifiers that we used, and then these were some of the narrow and broadband spectral indices that we used. Here's a table of the broadband and narrow band spectral indices. You know, of course, the broadband one, NDVI, the most prominent one with red and near infrared. And then, you know, we have some narrow band into PRI is a narrow band index using hyperspectral imagery. And then we have EVI, which is another broadband index. And then we have Chi and Sindri, which are narrow band indices, right? For the broadband indices, we had to average out for the blue, green, and red regions. For the blue, we used 400 to 500 nanometers and averaged the spectral values between those. And for red, we used 500 to 600. And for green, and for red, we use 600 to 700. And for NIR, we use 750 to 850 nanometers and average that to arrive at the red and NIR values for the calculation of our broadband indices. Each of those indices are useful for particular applications. Like you see here, NDVI is prominent for vegetation. The separation between vegetation and soil is maximal when you use NDVI, and then you have EVI is very effective in classifying high biomass regions in cultivated agricultural fields. Chi, which is our tillage specific index, and then we have our own MDRRL metric that we used. To summarize the results, as you can see here, these are our target classes that we were looking at: wheat, tobacco, legume, eggplant, and others. And you have all our indices. And this results essentially is showing the predictor importance. As you can see, PRI has, it kind of topped out in our predictions here, which is, as you can see, for wheat and for legume, PRI proved to be a very good predictive index. And MDRRL, it came in second for like tobacco and legume category, those two of our crop types. So PRI and MDRRL, were ranked as ranked really higher in the predictor importance when we used these indices for mapping these crop types. And then a look at classification accuracy here. We have these 4 machine learning algorithms, and then you have the ensemble algorithm here. So you can see the area under the curve for most of them, was over over 0.7. For most of them were over 0.7. When you have an area under the curve above 0.9, we classified that as a high performance one. 0.7 to 0.9 is reasonable moderate, and then below 7 is poor performance. The best performing models in this particular case, in mapping crop types on a district was our GLM and Maxent models. Maxent is outperformed GLM in our model predictions. But like I said, most individual models had an AUC value of greater than 0.7, fairly good prediction. Here is a map of the crop types that we were able to predict using the ensemble class. This is a output from an ensemble classifier here. Of course, we produced 5 binary maps for each target class. A binary map, what do we mean by that is that the binary classification is essentially presence or absence of these classes, right? The 5 binary maps, and then we combine those binary maps into a single map at the end. And then you can see the output right there on the left. So one classification using the present sampling data is a useful approach when you have limited field data. That is something that we identified through our work. It essentially reduced the noise, and it improved our prediction of all those crop types that we were looking at. And the selection of explanatory variables, sample size, and the size of the study extent is very critical. The explanatory variables and the sample size, is really critical in really achieving good results when it comes to our prediction of the crop types, right? But we can arguably say that OCC is the most suitable approach for mapping agricultural systems with limited field data from our study. And the continuous probability surfaces that are generated through this approach could provide a valuable depiction of the gradient of target classes. Instead of saying is present or absent, you have a gradient of target classes that is usually not provided by discrete maps. So again, that's one of the reasons why OCC is a suitable approach for mapping agricultural systems with limited field data. And then here's another thing. Continuous surfaces offer the user a gradient of confidence to interpret the ecotones that form at the agricultural interface, system interface. And it's also useful to classify complex surface patterns and mixed agricultural systems. That is another big advantage with OCC, is when you have mixed agricultural system, which is typical of Indian system, an one class classification approach might prove very beneficial there. Finally, we could also adjust the threshold, dependent trade-off between false positive and false negative results to actually improve the classification of agricultural parcels. It gives us the opportunity to adjust the method itself, lends us the opportunity to adjust the thresholds to, essentially improve our classification of agricultural parcels. So that was the first objective of the work that we proposed to do. The second objective was really mapping carbon in those agricultural systems. The first objective was to map the crop types in the area and map the agricultural systems in the area. And the second objective was to really map carbon sequestered under those systems. So in order to map carbon, one of the critical aspect of carbon mapping is getting a good representation of ground truth information. So that's where we had to visit India to get the ground truth data information for our soil carbon mapping. So the methodology that we followed to identify the point locations where we'll be collecting our ground truth data is what is called as conditioned latent hypercube sampling. It's a stratified random sampling. What does it do? Essentially, conditioned latent hypercube sampling strategy stratifies the attribute space. What do we mean by attribute space? In this case, in our case, the attribute space was provided by the different indices that we developed, NDVI, Chi, Sindri, and all those indices Dr. Salas had developed. So the attribute space, this particular algorithm, it is a statistical algorithm. It kind of stratifies the entire attribute space into clusters such that the clusters are maximally stratified. So if we go and sample within those clusters, we get a good representation of the variability of the image that we're looking at. Essentially, that is what condition latent hypercube sampling is doing. So so before we decided to come to India to get our ground truth sampling data, I mentioned it to Dr. Salas, and I asked Dr. Salas to come up with 1,000 points in the study area that we would like to come and collect ground truth data on. And I said, Dr. Salas, why don't you go ahead and create those 1,000 points using the variability inherent in the average imagery that we have. So he went ahead and created those 1,000 points in our study area. That's what you're looking at in this image. The red points are all of the 1,000 points, right? So I said, okay, that's good. So Dr. Salas, he reached India before us, and he started working on, collecting ground truth data with the support of course, with the support of Dr. Rucha Dave and her team. And I kept asking him over the phone when he was there. I said, Dr. Salas, how is the ground truth work going? He said, were you able to get to those points? He said, Dr. Shakti, yeah, it's good that we were able to come up with those beautiful points, but I'm facing some technical difficulties here. I'm unable to access some of the locations that we have identified in the map, right? And accessibility and complexity of local road networks would us to go and collect ground truth data from every point that we thought we would be collecting ground truth data from. So essentially what he was suggesting to me was I'm doing an intensive adaptive field or form level sampling. I said, that's good. You're doing, as long as you're trying to achieve, capture the variability in the areas of the study area, then that's good, Dr. Salas. That's a good, that's good. I'm satisfied with that, right? So he had to modify the sampling design in real time when he was collecting this ground truth data. So, and then he went ahead and he started collecting all those points, and we were so excited, about the data collection. And Brian and I joined the data collection work a little later. And, we were, the image that you're seeing is, these were all the soil samples that we collected in just one day. And here is our team, that really helped us. I'm really appreciative of all the support that we received from this team. And on the bottom left here, you see, we also visited Dr. Bhattacharya at his residence. And this is our data collection. This picture you're seeing here is a talk that I gave at National Bureau of Soil Survey and Land Use Planning regarding this work and the soil survey work that Brian and I are involved in. So everything was going well. And I said, this is amazing. You are working on collecting all this data. Right. And I said, Dr. Salas, can you, take the geocoordinates of those data and populate on top of the study area and show me where you've collected all those data? When we came to the US, and this is what we did. And I looked at this image and I said, man, this is good. This looks good. But did we capture all the variability that we were supposed to capture from the imagery? Well, I was little taken aback, and I said, oh, but in my heart, I'm thinking all is well, that's okay. We have collected, we have done a good job. We still collected 1,000 points, right, from this area. So when we overlaid on top of the, the points that we were where we intended to collect, those were the red points, and the yellow points were the points that we actually collected. So, I talked to Dr. Salas and I said, Dr. Salas, why don't you assess the reliability of the ground truth data that you've collected? Is there a way for us to assess it? How well is our data capturing the variability in the scene so that we can be confident when we map, when we take this data and map our carbon and map our crop types, right? So that was our next challenge, is in hyperspectral image analysis. One of the challenges that we face, remote sensing specialists face, is valid representation of the spatial variability of ground truth data, right? Is critical to predictive modeling using remotely sensed data. Often the source of uncertainty stems from suboptimal field sampling design. And most remote sensing literature, as you might have noticed already, deals with improving sampling technique rather than actually quantifying the errors and uncertainty associated with our sampling methodology, right? So we focus on improving our sampling technique, but we don't focus on quantifying the errors and uncertainty associated with our our sampling data. So it's very critical that we assess the reliability of ground truth data. So, that was our immediate objective, was to assess the reliability of the collected ground truth data before even we ventured into mapping soil carbon in the region. So I said, Dr. Salas, we have to look into this. We have to assess the reliability of the ground truth data. And then, so Dr. Salas came up with this idea of quantifying the uncertainty of those points data that we have collected in the study region using Gaussian simulation and geostatistics. Gaussian simulation and geostatistics, and the goal was also to identify optimal number of samples to capture the variability in the study area. So the idea was to really take the average NG imagery and take the field points that we collected and take the conditional latent hypercube points that the machine told us to collect, to capture the variability efficiently. And then, Dr. Salas took those points and he simulated all of those indices that we were looking at using Gaussian simulation. He simulated all of those indices, and then you have the measured values, which is the field points and the CLHS points are directly derived from average data. And then, so when what we did was we compared our simulated indices versus our measured indices using a metric called as mean absolute error. And then we also created variograms from the measured indices, we developed or built experimental variograms, and we quantified the spatial heterogeneity. Essentially, the goal was to see how close the spatial heterogeneity was for the variogram that was developed using CLHS points and field data points that we collected. Okay, and these were some of the indices that we used, like our previous exercise, but we added a couple of other soil indices, this is a bare soil index, and this is a modified soil vegetation index, in addition to the vegetation indexes the indices that we were using. Okay, so this is a quick overview of the variogram. As many of you might already know, we're working in remote sensing. You have the lag distance on the x-axis, and you have the semi-variance on the y-axis, right? And this is a plot, actually, essentially a plot of the average distance between the average difference between the data points, squared average distance between the data points plotted against the distance and the semi-variance on the y-axis, right? And this curve gives us an idea about the spatial variability inherent in any image. What this graph is showing us is essentially a measure of spatial autocorrelation. Things that are closer to each other are more similar than the things that are farther apart. So the data points that are closer to each other are more similar than the data points that are farther apart in a spatial scale. So this is a plot that shows the spatial autocorrelation. As you can see, as we go away of the distance, when the distance between the points increases, there is a increase in the spatial variability there, semi-variance there, and then it plateaus after a point. So this portion here is the nugget, which essentially quantifies the inherent variability, the variability that is not identified, or hidden variability, which is the nugget value, and then you have the structured variability, up until here. The entire, this length is called as the sill. So just by looking, and then your ranges between the, the point where it starts and where it plateaus, gives us the range of the variogram. So using these metrics and looking at the shape of the variogram, we can essentially say if our CLHS data points and ground truth data points are, how close they are to each other. And of course, with the mean absolute error values, we were able to compute the mean absolute error using this metric here. I don't want to go into the details of that. Mean absolute error is really indicating the average difference between the simulated index from CLHS and simulated index from ground truth data. And here are some plots. These are all our variograms. As you can see, pretty much for both ground truth and condition latent hypercube, as you can see, they follow pretty closely to each other, right? They look very similar. The spatial structure looks very similar, except for PRI. That might, the reason might be, the mixed practices that are available that were there in the form when we were trying to sample. This was primarily due to the sampling discrepancies when we were sampling ground truth data, because we were trying to sample from closer, we sampled at closer locations to each other. So that could have caused that difference. But more or less, the spectral shape of the variograms were very similar. And so were the mean absolute error values for all of those indices using condition latent hypercube and the ground truth or field points. The result also, this result also helped us identify an optimal number of sampling points that would have the minimum mean absolute error between those 2 points, which was around 700 sample points. So this exercise was worthwhile to really look at, the reliability of the ground truth data that we collected in India. Our next step is to actually use those points and try and map carbon in those systems that we have identified initially. So on a lighter note, I would like to end my talk on a lighter note. The samples that we collected, it took about 8 months to get the samples here in the United States. We had to go through customs and all that. But I had to change multiple carriers to bring the samples in to get it analyzed for carbon in the US. But one interesting story was when I was trying to get the samples in, I happened to contact this customer service person at one of the carrier offices there in Gujarat, and I started talking to him in Hindi. I'm glad that I knew a little bit of Hindi. Then I started talking to him in Hindi, and the sample got stuck in a location where I didn't even know. So I was trying to track down the samples. The samples left AAU, but it got stuck somewhere else. And I tried to call this the customer service rep, and he essentially, and I asked him, hey, where is the sample? And I kept, calling him again and again, and because it was getting delayed. And finally, he got fed up with me, and then he essentially started talking to me in Gujarati. The moment I started talking to him in Hindi, he would start, he would talk to me in Gujarati, and I couldn't make any progress. And I had to, switch carriers. I'll leave the names of the carriers unnamed here, but I had to switch carriers and get the samples in to get it analyzed. So, but I'm really excited to continue that work with AAU and ISRO, and thanks for all the support that we have received there from AAU on this project. I'd like to close my talk with acknowledgements. I'd really like to thank Dr. Rucha, and all her team, every one of them, Parsh, and Bilal, and Prachi, and Gaurav, Dimple, Saif, and Nikunj, was the driver, and Armuga and Saif. And also I'd like to take this opportunity to thank NASA for providing us the support to work on this project. Dr. Robert Green at NASA, Dr. Bhattacharya with ISRO, Dr. Rojalin Tripathi and Ayan Das and Rahul Nigam. So with that, thank you so much for providing me the opportunity to come and briefly share about the work of partnership that we have with AAU on remote sensing for agriculture. I'll pause here and I'm available here to take any questions.
Yeah, thank you very much, Dr. Shakti, for a very nice and informative presentation. And yes, we have some questions. So I'll just post it in chat box. Maybe it would be, are you comfortable with that, or should I?
Okay, let me see.
Yeah. So the first is, so what is the maximum resolution we have now for remote sensing of vegetation? It starts from there.
Okay, let me see. Let me open up the chat box here for a moment.
Yes.
Let me stop sharing, that way I'll be able to, okay, that's good. So for some of the technological questions, I might, I have an expert here with, in Dr. Salas. He has worked on these spectral indices. Dr. Salas, do you have an answer to that question that Dr. Rucha just posed?
Yeah, I think, hi everyone. So I think it really based on what do you want to see or your output. For instance, if you want to map in a much global scale, you can use a much broader satellite image for mapping vegetation. In the case of, for instance, MODIS has around 250 kilometers spatial resolution, and it maps out in a global scale. But if you want to map vegetation, for instance, in a much regional scale, Landsat, you could use Landsat, which is has a 30-meter spatial resolution, or SPOT, for instance, that has a much finer resolution than Landsat, which is like 20. And there is also a much finer resolution, like not maybe like commercially available satellites, for instance, like Iconos, which is, I think, has a much better revisit period, So it really depends on what you want to see. So if you want to see a much higher resolution, a much smaller scale, then you use satellite images that captures a much smaller spatial resolution. But if you want to see a much broader scale, use it in much broader scale, like global scale, then you could use a much higher spatial resolution, like MODIS, for instance, or Landsat.
Okay. And Sentinel-2 has a finer resolution than Landsat 2, right? I've seen that people have used Sentinel-2 for mapping wetland vegetation, for example.
Yeah,
Brian,
there are also commercial satellites like QuickBird, that has 2 meters. That's very good for mapping fields, for instance, or farms.
Okay. Okay, and the next question is, what might be the basic initiatives for implementing actually these technologies in developing countries?
Okay, so let me go back to the question here. What might be
for implementing these technologies in developing countries?
Basic initiatives for implementing these technologies in developing countries, right?
Yes.
That's a broad question. I think, partnerships are critical. Like what we're doing, Rucha, is that, learning from each other.
Yeah.
It's like Brian mentioned during his talk, we're making some great strides and advancements are happening every day. And the literature is just exploding in this area. So there's a lot of information out there. The key thing is really like, working together on these areas. And there are multiple organizations that support those, multi-country collaborations, that could really play a critical role in, implementing these technologies in developing countries. I had a conversation with Bahamas, the Ministry of Agriculture there, and I mean, these developing countries might not have all the resources like we do in developed countries in other places. The only way to achieve, implement these technologies in developing countries, India might be doing a lot better there. But when you really start talking about some developing countries where they don't have those resources to pull, and even the knowledge base, I think the critical thing there is to really establish those partnerships with people who have worked in those areas and and make some progress there. Brian, do you have any thoughts there? Like, what are...
I agree with you entirely. I think we learn from each other. We learn collaboratively. I think certainly Shakti and I and Eric, we learned a lot more than Rucha and her team learned from us. We probably learned some new jokes, but we I think doing things together. I don't see a difference between developed and developing countries when it comes to expertise and brain power. I've just been so impressed with what we've seen in India, and the work that's being done, and also the enthusiasm. And I think a lot of that comes out of the fact that the need to get things done is very strong. So I know that in the 1960s, I was talking to Dr. Lal about in the early 1960s. He went to a college in Punjab that eventually become the Agricultural University. Then it wasn't even a university, and Ohio State was involved in trying to get that institution to become a university, to become a degree granting institution. And now, though, I think these great universities are all over India, and there's fantastic work being done. So I don't think there's anything special that needs to be done differently. But I think collaboration, I think working together, and I think sharing is probably the most important thing, sharing data, because Shakti pointed out, we're very fortunate that with a lot of remote sensing data in the United States, it's free. If we have to go, sure, we can get QuickBird and Iconis data and Worldview, things like that are higher resolution if we really need them. But we have such a great range of products and interpretations and ways to use them that NASA and the partnerships in the United States have made available. And that data is worldwide too. It's not just restricted to the United States. Like everything from the original digital elevation models and the SRTM from the space shuttle, and now the Europeans are in on that. I mean, you can spend a lot of money on data, but the more we can actually share our techniques and algorithms and methods, the better we can advance the science and the applications.
Yeah, definitely. And the next question is, how can we use Google Earth Engine for a purpose? For the study which you have shown, can we use Google Earth Engine for that? Shakti, this is for you, maybe.
Yeah, so I think, we were exploring that. We haven't, Brian and I have not used Google Earth Engine before. In fact, Brian and we wrote another grant recently to map hydrologic conditions in the soils and map wetland vegetation, and also, kind of like map ecosystem. What is it called, Brian? Is it like ecosystem?
Ecological sites.
Ecological sites. Yes, that's right. Thank you. So ecological sites, right? And we, in that proposal, actually, we said like we'll be using Google Earth Engine, because Google Earth Engine is so powerful. You have all these data sets readily available, right? Satellite data sets that are readily available, and the power of using those data sets and in the back end, the processing is done in the back end in the Google Earth Engine. That saves the computational needs that we would otherwise need when we are running all those models in our computer. So certainly, I think that's the future, actually, using Google Earth Engine and similar things where all the computing is done in the cloud, using all these humongous data that we're getting from satellite imageries. I think, that's the future of, tying machine learning and satellite space technology and interfaces such as Google Earth Engine that would pave way for doing all those kinds of, predictions. So yeah, so the question was, I don't know, what was the question again?
How can we use Google Earth Engine for a purpose?
Of course, yes. The short answer is yes.
Okay.
And
Yes, you can use.
So you can see the next question that is from Nahib Cast itself. So how much carbon did you end up smuggling through successfully?
I have actually done a calculation while Shakti was talking then.
Yeah,
So we had
I'll do a
1,000 samples, approximately
I should
500 grams, approximately 500 grams per sample. If we multiply that out at an average carbon content of 2%, we smuggled about 10 kilograms of carbon. I'm not sure what the penalty is for 10 kilograms. I think that's more than personal use. So we probably could get into trouble.
Okay.
Yeah, that's okay.
So which data give you most efficient results from both countries' data? That is the question.
Which data gave you most efficient results from both countries' data? So I'm trying to understand that question. So
Yeah,
can you?
it may be with the reference to ground truth data.
Okay, which data gave you most efficient results from both countries' data? Which are? Do you want to take a shot at that, Brian?
Yeah.
Or Eric? Do you follow that question? I'm still trying to, decipher that question.
Because India and USA both are having different land use patterns, so maybe it is with reference to that ground truth data. Maybe what I understood.
Yeah, I think ground truth data is going to be important everywhere, but I think it's especially true when you've got complex landscapes and land use patterns. I think we haven't done the same kind of mapping with the same outcomes in both places. So in the United States, we've mostly been mapping soil classes, and in India, we're mapping crop types and carbon. So there's a bit of a difference. So I think different data is needed for each output.
And just to add, I think that the data, the method that we applied, for instance, in the data set for India, can also be applied to any data from other countries as well. So, for instance, when we validated the ground truth data that we collected from India, the methodology can also be applied to any other data set collected from other countries. So,
okay. Can you please tell about central pivot irrigation using satellite?
Yeah, that's a great question, Brian. Do you have any input there? Do you have any experience in that area? Central pivot, mostly in the Midwest, not in Nebraska and other regions, right?
Yeah, well, I know that moisture sensing is used even for control. Satellite moisture sensing has been used for control of central pivot irrigators. So, when to turn it on, when to turn it off, even, depending on how much moisture is in the soil. So, moisture algorithms, SMAP data, SMAP data is probably a bit coarse, but, to actually control an individual irrigated area. But certainly some of the vegetation indices can be used to monitor crop stress. So if the crop is in need of moisture, particularly if you've got fairly fine temporal resolution. So data that's got fine temporal resolution can be used, and it is being used out in the west of the United States. But I don't know more than that. Just generally, I know that data is being used.
Okay, and there is another question. Can we consider OCC more informative with respect to other data imputation techniques?
And what are the criteria for picking explanatory
Yes,
data?
yes.
Right? So I think Dr. Salas, you're an expert in that, OCC. What were your thoughts on that?
I think if you compare OCC to other techniques, I think OCC doesn't only apply for vegetation mapping, for instance. It could be applied to any other types of land use classes. For instance, it has been used to map wetlands, and it was very successful in mapping wetlands. So I think there's the benefit of using OCC compared to other techniques, but OCC is really a broad application as well, and it could be applied to any types of land use classes, mapping land use classes. Now,
but the challenge really is sometimes, again, like, OCC might be beneficial in our case when we are working with limited data set, but that might, I mean, because, you're creating, generating these layers, predictive layers one at a time, and then you're summarizing that information. But when you have a large amount of training data set, at that point, I think there might be other techniques that are better, might perform better than OCC. So correct. I think it is important that we assess, the benefits of each of those machine learning techniques that we're using on a case-by-case basis. It's very, so we cannot generalize and say OCC is going to be better for every, application. So the machine learning techniques that might be beneficial under certain circumstances might not be suitable at other circumstances. Do you agree, Dr. Salas, that way? So it's,
yep. Yeah, I agree. I do agree. Yep.
Not like a blanket recommendation for.
And I would add that there is always information in data, and if you use OCC, you're going to get different outcomes, but there is going to be something in there that might be useful to you compared to other methods. So it's always useful to have multiple methods, because you might learn, for example, OCC, I think you mentioned, it can be very interesting at the boundaries, where you've got mixed vegetation, for example, something like that. It tells you something about the interspersing of the class that you're predicting that you might not find. And the same thing might go the other way too. So I think it's always good to do comparisons between different methods. And there are particular characteristics that relate to each method that people need to understand and know. And we're only just starting to learn what those are, I think.
So the next question is how space technology and machine learning aid up to produce secondary metabolites from plants.
Oh, I think there's still another question before that, right? Like, what's the criteria of picking
explanatory variables? Yeah.
Yeah. I think in this case, in this case, what we did was we based our selection on the efficiency of how these models would be efficient in modeling limited data sets. So that's basically, in our case, we used like 4 or 5 machine learning techniques. And all these 4 or 5 machine learning techniques were actually very efficient in modeling very limited data sets. So that is one of the basis of why we selected these learning methods. Now, in the case of variables, it also depends, again, it depends on your objectives. In this case, we wanted to map vegetation, which is located in a more sparse, distributed sparsely in a study area. So we selected predictor variables based on which indices that are related to vegetation, indices related to tillage, indices related to soil. That's why we have MSAVI. That's why we have a bare soil index. So the selection of the variables would really depend on what you want to map out, what you want to see. So if there would be vegetation, you might include NDVI or EVI. So are these efficient? Because based on research and publication that's been established already, NDVI is really good for vegetative mapping. So you might include NDVI. Now you can actually include as many variables as you want, because in a machine learning technique, it could actually just detect which one is better. You can run as maybe 10 variables, or you can run 250 variables. It might take time if you put many variables in the algorithm, but in the end, it would actually tell you which of these variables are important for mapping those land use classes. I think the machine learning will do the technique for you in selecting which a variable is better than the other. I hope I answered that question.
Yeah, yeah. So the next is this: how space technology and machine learning aid up to produce secondary metabolites from plants.
Dr. Sakti?
Yeah, is the question
What
is the
is
question
metabolites?
asking like can we predict secondary metabolites in plants using space technology and machine learning? Is
Yeah,
that the question?
it is written as produce secondary metabolites from plants.
So I guess, you know,
Yeah.
if the question is really identifying secondary
Yeah.
metabolites in plants, that is I don't have any experience in that area, but well, one of the recent places that let me turn my video on. So an area that I'm interested in right now, Brian, you know, we at Central State, we have hemp growing. We have a hemp specialist. Hemp is kind of a medicinal plant used for medicine. And one of the key metabolites in the hemp is a THC, you know, content. The THC content has to be less than 0.3% in hemp production. So if it exceeds 0.3%, then it's illegal and becomes marijuana, which is a drug actually, you know, which is illegal to grow. So one of the things that we're looking into is, you know, really we're seeing if there is a way for us to predict those metabolites using not space technology, but using proximal sensing.
Okay.
So it's definitely possible, but I am not aware. That does not mean that there isn't any, but I'm not aware of, you know, people using it, you know, for identifying secondary metabolites. Brian, are you using space technology?
I don't. I think the spatial resolution of most, at least satellite and airborne sensors, is not going to be helpful for something that is going to vary at the plant level. But I think that the basic technology of sensing, of remote sensing, is more than likely would be very helpful. But you'll be mostly using proximal, multi, and hyperspectral scanners in the field, and there are various other scanners too that go beyond the visible and infrared that may be useful. But we're certainly you're talking to mostly soil scientists here. We're not that expert at what's happening in the plant, I guess.
But I think drone-based technology, Brian, I think, you know, can really supplement that kind of work, because we're doing
the work that's done in precision agriculture, you know, with tractor-based and gantry-based systems, you know, where you take during the crop growth, you actually take something over the top of the crop and measure things, but much closer, so that you can resolve things at the plant, individual plant, or at least row level would be helpful. Yeah.
Okay. So the last question is, what is the feasibility of Indian airborne imaging systems for Earth observation when cost of collecting EO information is an economic constraint?
Well, I'm going to turn that back to our hosts, because I at least have only just started to learn about Indian EO systems. So I would be very interested to hear what you folks think about the feasibility of your own EO information for some of this kind of stuff. And the question is airborne EO. So you know, right now, ARIS, it's a pretty expensive proposition to put up a flight, right? Is there any opportunity for India to develop a similar system that they could run themselves? So I'll turn this question back to you.
Yeah.
Yeah.
Do we have anyone from ISRO attending the webinar?
Right now, I don't know. Not in the Zoom platform, but yes.
I wish Dr. Bhattacharya was here. He probably would have.
Yeah.
And then,
So there are actually so many questions here. Now it is emerging, but maybe we are time is over almost. Can we take 1-2 questions or?
okay, go ahead. Yeah.
I would
Yes,
suggest
this
if there's
is.
any
I'll just selected questions. I'm just taking.
okay.
So how these Everest NG data can be used in the phenological study.
Dr. Salas.
Phenological studies involved actually a temporal way of collecting data. So depending really of how, in the case of the average NG in India, we have collected 2, right? I think there were 2 collections already that has been done. I think that was the 2017 and 2018. I think that was the collection dates.
Yes.
So if you want to do
16
some
and 19.
phenological studies, like looking at how, phenology changes over time, then I don't think it might be enough to really look at the, except of course, if you look in terms of seasonal phenology, maybe you can have like 2, or, how it changes from, I don't know, the seasons of India. Maybe there's just like 2 seasons in India. So
No.
maybe, maybe if you have.
I put in my 2 cents here, and the temporal resolution of average data is almost infinite, because typically there's one flight and that's all the data we have to deal with. So most phenological studies need some kind of temporal resolution, multiple data sets. And as Dr. Salas said, we're lucky to have 2 different dates, and not only that, but the 2 dates were fairly close together. Where crops were pretty much in the same phenological stage. So, we can't really use them for that process. I don't think an airborne hyperspectral scanner is the way to get phenological data. It doesn't strike me as being very useful.
But one thing though, Brian, like, if there are phenological differences within the imagery, if there are
I agree. So spatial differences, particularly at the scale of average, which is quite high resolution compared to most satellite sensors, that spatial resolution allows you to see, for example, the variability of crop health in a field, or from field to field, that might indicate things like waterlogging or drought, or soil moisture problems, or even diseases and insect pests that are spatially distributed. So I agree with you. Differences on spatial scales could be easily, AVERS would be an excellent data set for that.
And it's, like if the planting dates are different, let's say, based on the environmental variables, if climate and if there are differences in planting dates, and I think if average gets us a good coverage, it should be pretty useful to.
So within the season, you can have different phenological stages. At least for Indian context, we can have. I don't know about the USA situation, but in India, we have different dates of sowing for the same crop within a same season. So it might be possible for some of the crops. And this is the last question. I'm just in irrigation experiment, where exactly NDVI value is helpful?
Irrigation is more on the water, right? So NDVI, if you have NDVI for water, it must be very, very low. So NDVI low values of, like, you can, you can use NDVI because for instance, excluding water in the classification, because low value NDVIs are usually the water features on the image, for instance. But you might be using some other indices as well, not just the NDVI. Since as we have, as we've been discussing machine learning techniques, you can use different indices, for instance, to detect water features in your images, and then and you run machine learning to do that. Not just NDVI. NDVI may give you, because NDVI is really designed for vegetation purposes, where higher values of NDVI would detect, the vegetative part of the imagery. But for soil, for water features, there might be some less discrimination when it comes to water, because NDVI is not really for water mapping.
But perhaps the question also relates to irrigation scheduling and the amount of irrigation water that needs to be applied, and that can definitely be conditioned by the crop greenness, which really indicates when the crop's under stress. So and NDVI has been used that way for irrigation scheduling, in crops over large areas. So where to move your irrigator. That's what I was talking about before. When to switch your irrigation on, when to switch it off. If you've got good temporal resolution, then you can actually use multiple NDVI measurements to determine how often you need to be irrigated. So it can be helpful.
Okay. I think, and also I think, for irrigation scheduling and irrigation experiments, PRI might be a better indicator, because it's a photochemical reflective index, which quantifies evapotranspiration. So under, when you have irrigation experiments going on, there is always those differences in evapotranspiration happening, based on the salt water potential and, all that. So I think, photochemical reflectance index would be a better index for, for using under those circumstances. NDVI certainly, yes, it's going to give us information about greenness, but PRI is another thing. And I think we found PRI to be a good indicator, right, Eric, in our research. So that's another potential index that might be useful.
Okay. I think we have been ended up with the questions, and now we shall conclude this session, first session, technical session. So I'm very much thankful to Dr. Shakti for very elaborative session, very informative session also. And on a lighter note, someone has asked that question also: are you teaching every day? So I forgot to put that question. So, so are you teaching every day? So obviously your explanation was like teaching itself. So thank you very much for the learning session for us. And thanks to Dr. Brian and Dr. Eric and Dr. Shakti. And thanks for waking up till almost it's, what is the time? Almost it's 3 midnight.
2:30 a.m.
Yeah, 2:30 a.m. Yeah. So thank you very much. And now we'll be moving toward the next session. It is at 3 o'clock in the afternoon in India. So you must be sleeping at that time. So is there anything from Dr. R.S. Pundir? Are you there? Okay, they might be somewhere. Okay, so shall I conclude the session now, Dr. Shakti?
Yeah, thank you so much for having us. Appreciate you giving us the time to talk to you all.
Thank you very much. Yeah.
Thanks, Tucha.
Thanks, Brian. Thanks.
Great to see you all. Thank you very much.
Yeah.